but it is an honor to be able to introduce a famous guy who's now at UQ, the University of Queensland. Been there about a year. He has 2 hats on in the School of Chemical Engineering and also at the Dow Centre for Sustainable Engineering and Innovation, which covers also nuclear themes. Prior to that, he was at Santa Barbara, an interesting profile anyway. You're a medical doctor and also an engineer, and started out in the nuclear business. Had a bunch of entrepreneurial activities while you were in Santa Barbara, and now you're in Queensland, and a new era has started. And we're looking very much forward to your talk, Mr. McFarland.
Thank you very much. It's a pleasure to be here. I've actually hadn't been to Sellafield before, so I've seen some of your other sites, and it was really quite a walk through the history of nuclear science the last few days. I have just recently gone to Queensland, and based on a generous gift from the Dow Chemical company that basically gave a no strings attached gift to the university to start a center on what they called sustainable engineering innovation, which is a lot of words. And my intent was actually to try to make it mean something. And when they were recruiting me, they didn't really have a plan, so I was able to shape the program, and the idea was to look beyond the horizon of the R&D segments of the chemical industry, or even industry in general, to look a little bit at the future and what would be important sustainably in terms of sustainable societies. And for me, nuclear science had to be there. There was no way that I could envision a real sustainable future in the long run without having nuclear as part of it. And you're going to hear today a little bit about what we've been evolving into, the contribution that we might be able to make, and it draws on experience that I've had working in the chemical industry, and how one might use some of the learnings from the chemical industry to make nuclear potentially even profitable today. So I'm going to talk about some of the things that we've been thinking about and how to do that. I want to start by saying that for me, and was the reason I went to college, I was always impressed with the amazing energy associated with nuclear reactions, and I believe today, as much as I believed in those days, that nuclear produced energy and power was something that would be something good for the world. And it would be something that, in particular, given the world dynamics today, that democratic nations actually are falling behind on. And if I can do anything as part of the center, I want to figure out ways that democratic nations can participate rather than non-democratic nations in a nuclear future. So I'm going to talk about why Western democracies aren't aggressively adopting nuclear power, and talk about potentially a change in how we approach the tactics and strategy to achieve a goal. And then I'm going to use the example of co-production of chemicals as a potential way of making nuclear reactions something that would be valuable today, in spite of very, very low fossil fuel costs. And I'll give you some examples. So if you read the World Nuclear Association, nuclear power is cost competitive with other forms of electricity generation. The caveat, of course, is that except where there is direct access to low-cost fossil fuels, which is everywhere. So it's not cost-effective is the right answer. If you look at the numbers that people are putting out into the open literature, and these are pretty close to what they really are. Sandman in China, built by Chicago Bridge and Iron, came in at about $5.9 billion, including financing costs. That's about $3 a watt output in cost. It took about 60 months to build. So that's not so bad. Taishan isn't finished yet. It's probably going to come in maybe a little bit cheaper with the Areva EPR design. Areva didn't make any money on this job, but nonetheless, it still looks not so bad. Probably is going to take about 45 months to complete, but probably coming in at a pretty reasonable cost. In the US, however, Vogtle 3 and 4 is already looking like it's going to be close to $8 a watt. And that's early. It's not done. And so it's only going to go up from there. It's not going to come down. So these kinds of costs are really pretty prohibitive in terms of producing power. And essentially all projects, including the ones in China, always escalate. I mean, you never see a case where they're being built under budget. And so all of these costs are quite high. And when you're looking at a financial risk of putting billions of dollars at stake, and you have these kinds of risk factors, people end up not making decisions. And I think that's going to be true here in the UK, where they claim they're going to be doing some new build, but when the people have to write checks with these kinds of risks, unless they're backstopped by the government, they're not going to be making these kinds of decisions. Not that people don't spend billions of dollars. People spend billions of dollars all the time on big projects, but they don't want to not make any money when they do that. The setting, though, in terms of the competition, is that coal and gas are going to remain inexpensive. They're going to remain inexpensive for our lifetimes and probably our kids' lifetimes. And if you look at just the OPEX cost for fuel, it's going to be around 6 cents a kilowatt hour globally. Some places higher, some places lower. And almost everywhere with the most advanced technology with fossil fuels, they're coming in at about $1 a watt. So that's not a lot of money to be spending for producing power, and because power has to be cheap, that's what it needs to cost. And the cost of $1 a watt is using advanced stuff. You're using supercritical steam, combined cycle, all the state-of-the-art types of power technologies being used, and it's still coming in at very, very low capital costs. On dollars per watt of thermal, it's only about 30 cents a watt thermal production. If you look at what people are doing in the nuclear space, if you look at all the Gen 4 designs, they're all terrific in terms of addressing concerns on safety, better use of fuel, all kinds of new bells and whistles that make them nice engineering designs, but unfortunately none of them are going to be cheaper than the old designs. They're all going to be, in fact, more expensive. There's been talk about co-producing things like desalinated water, and there was a project in Kazakhstan to take a 1,000 megawatt reactor and derate it a little bit and make do desal. With power at 1,000 megawatts, 333 megawatts electric, that's about $83 million a year in revenue. Or in the case of this plant where they derated it, they made 120,000 meters cubed per day of desalinated water, but water is produced everywhere in the world for $1 a meter cubed. So desal only, in fact, reduces your total revenue. So you might as well just sell the power. Desalinated water isn't valuable, and we know how to make it. It's off-the-shelf equipment at $1 a meter cubed, and so you don't really gain anything by making desalinated water. There's been a big thrust to make hydrogen. Well, hydrogen is equally as low cost as electricity, so if you derate a reactor or even use some of just the thermal waste heat, you're making something that isn't worth very much, about the same as the electricity. So the product of making hydrogen isn't necessarily a good product to be making with nuclear reactors. It's not going to change the attractiveness of the investment in terms of the investment community. In the end of the day, you're making steam. And so if you have a megawatt of thermal energy, 30% efficiency to make the electricity, the most you're going to make in revenue, if that's assuming you can get 10 cents a kilowatt hour, which is generous, is you're going to make $250,000 a year per megawatt, and it's probably going to be about half that because no one's going to pay you 10 cents a megawatt, 10 cents a kilowatt hour for electricity. So you don't have a lot of revenue that you're going to be making when you make steam. And whether you make it from burning lots of coal or natural gas, or if you make it from uranium, you're still making the same product. So the piece of capital that you're making to make that revenue can't cost more than about $1 a watt. That's just the basic economics, and you can't change that. So if one's looking at making an investment to produce power, even if you look at carbon taxes of $30 or $40 a ton, it's still not going to work economically very well. So you can look at what happened in biofuels in the US as kind of a case study and learn something from what they did. Everyone was going to take biomass and make it into fuels, and the argument was it's a big giant market. We can make this, and it's going to be green, and people are going to pay a premium. It's a relatively complex process, though, to take things that don't look at all like fuels and make them into fuels. It's lots of other issues with gathering sufficient feedstock, and there's other competing processes. So what the biofuels industry in the US that had all the promise has done is they decided they could actually make money by making chemicals. And in fact, that's what they've all done, is all these companies, the ones that have survived anyway, have changed their business model so that they can make something with basically the same amount of capital that has more revenue. And the ones that are surviving are doing that. They're making chemicals, and particularly the chemicals that have some unique feature that makes them look like the feedstock. Because in chemical transformation, you don't like to do lots and lots of steps. You want to do a few steps and make it something that looks pretty much like the feedstock. When you look at the things that you might make in the chemical space, molecular pharmaceuticals are the highest value at many millions of dollars per kilogram many times. And then the intermediate chemicals are a lot lower value. And this is in the blue dots are price per kilogram, and the green are dollars per mole. And fuel is the cheapest thing basically you can make. There's some commodity chemicals that are pretty close, but at least you get maybe a factor of 2 in value improvement if you make chemicals rather than fuels. And by the way, the volumes are pretty big for a lot of these commodity chemicals. So you have a big advantage that they're large volume. So what happened with the biofuels industry is they took unique features of biomass and they tried to match that to unique chemicals to give them the most value. But in nuclear reactions, what we end up doing is we take fission and we make heat at electron volt type energies. And so you've taken all of the good stuff out of nuclear reactions and just basically thermalized it to make it no more valuable than doing chemical reactions. But if you look at what's unique about nuclear reactions, you have fission fragments at 1,000,000 electron volts, you have ionizing radiation at 1,000,000 electron volts. That's unique. That's something that's special that you can't do in other ways. So when you look at what you might make with nuclear reactions, the things that are the highest value are the things like isotopes. Isotopes are going to give you the highest value, though the market's relatively small, and maybe neutrons, if you want to activate silicon and make phosphorus for doped silicon. These kinds of things are unique to nuclear reactions. You aren't going to get neutrons from somewhere else. In the middle, there's cost-advantaged products of nuclear reactions like ionizing radiation. You can make ionizing radiation with other means. You can use electron beams and so forth to make ionizing radiation, but it's still potentially cost-advantaged to do it with a nuclear reaction. The worst thing you can do is make heat, because there's lots of competition, and it's not the best way you can make it. So with isotope production, you're fortunate you get a gram per day per megawatt, and in the end, a lot of these isotopes are very valuable, hundreds of thousands of dollars a gram, and you're making a gram of them per day, per megawatt. So you have lots of options to sell isotopes, and there's many of these that are valued by the medical industry and in the industrial pharmaceutical or chemical area. They use them for tracers in the petrochemical areas. So these can have some significant value. And they are the highest value thing you could possibly make with nuclear reactors. So isotopes are a big target, and there's companies that do this. Nordium makes about $300 million a year, making xenon and iodine. Primarily moly is the biggest market, moly 99. And there's a big need coming up as research reactors that make moly are being shut down. So there's a big need for making this very valuable isotope. And if you have this reactor now and you have an option to make a megawatt of thermal energy or make a gram of fission fragments per megawatt per day and possibly make millions of dollars rather than only $250,000 a year per megawatt, you're going to choose to make isotopes, because that's a better value proposition for basically the same piece of capital investment. So who wouldn't want to do it? But the problem is that there's lots of other ways that are driving people to make this, because it's too much of a hassle to use a nuclear reactor. So people are using non-reactor sources to make isotopes. The other thing about isotopes is it won't finance new reactor development. You'd fill the market with one large reactor. So no one's going to finance new reactor development with the idea that isotopes is going to carry it, because it won't do it. Looking at the cost advantage products that you might be able to make use of, and these are the ionizing radiations, the idea that we're looking at is there chemicals that are uniquely suited to radiation chemistry that might have enough value and have your reactor or your nuclear reaction source or your nuclear isotopes as being the preferred source. And this has been around for a long time. Radiolysis of water was observed in 1914. And we know that there's a lot of things one can make through radiolysis. The critical factor, which I'll come back to, is G, the micromoles of product per joule absorbed. And so different chemistries have different yields of products per joule absorbed. It depends a little bit on the radiation but we'll just use that as a measure for a minute. Now, there's an enormous history in radiation chemistry. You all have done a lot here. I know you have faculty members that are very active and leaders in this space. Generally, though, a lot of the work that was done with the idea that you're going to look at processes that are related to the operation of the reactor. What's happening in the coolant, what's happening in the materials, how are we going to make use of this in terms of making the power reactor run better. There's been some work, and back in the 60s or so, all the oil companies thought that nuclear power was going to take off and they were going to have lots of radiation sources. So the oil companies, in fact, looked at things like what they call cold cracking, using radiation to do petrochemical processing. There was some work, but not a lot. Certainly not a lot of fundamental work, not a lot of optimization work. But lots of things have been irradiated, and you can make lots of products. Probably not necessary for this group, but typically I'll explain it to people that if you have 100 kilowatts of heat and you put it into a reactor that has water flowing through it, you make hot water. And don't make any hydrogen or oxygen. But if you irradiate that same reactor with 100 kilowatts of gamma radiation at 1 MeV, you'll make hotter water, less hot than the case of heat, but you'll make some hydrogen and oxygen. And so this idea that you're going to be able to do non-equilibrium chemistry potentially has some value. And the idea is to take advantage of kinetic direction of reactions where you don't have to worry about a back reaction because you're running the reaction at temperatures that the back reaction may be disfavored, like in the case of making hydrogen and oxygen. You do that in a room temperature glass of water. Hydrogen and oxygen won't recombine at room temperature, even though thermodynamically they'd like to. So you don't have a pathway to recombine. And so this can allow you to play some games and give you another knob in chemical processing. One way to do it is to adopt some of the things that people have used for solar conversion or making chemicals using photoelectrochemistry, where either you can use a scintillator and convert your gamma rays into visible light and do redox chemistry to make hydrogen and oxygen. I wouldn't choose that, but you could make it. Or you can have wider gap materials and you can make chlorine and halogens and other things. So that you could just use redox chemistry. The problem with this is the G's are typically limited to about 10 divided by the band gap in energy, or in electron volts. So you're limited to G's of about 10 at most. You won't get a lot of product for your radiation source. Now, when you enable chain reactions, though, you can get G's that are extremely high. So with the chain reactions, especially if you use that as an initiation process, you can get G factors of 100 to 1,000,000. And these have been demonstrated in certain systems. And the way to think about it from a chemical productivity point of view is that roughly 3 times the G factor is the number of kilotons per year you can make per megawatt of gamma. Now, typically a commercial chemical process makes about 10 to 100 kilotons per year. A big one makes 1,000,000 kilotons per year, a few of those. But you're looking for things that would give you about at least 10 kilotons per year of a mid-range chemical to make it interesting. And so you're going to be able to get reasonable amounts of yield from G factors that are quite achievable from a lot of chemistry that I'll talk about in a minute. So Dow Chemical was one of the first companies that, in fact, to use gamma radiation to make a commodity chemical. At the time, ethyl bromide was used as a gasoline additive when people used lead in their gasoline. And so they reacted hydrogen bromide with ethylene, and they had G factors of about 10 to the 3, 10 to the 4. They produced commercial quantities, and it used a cobalt-60 source as the gamma radiation source. And by the way, that source size to make a commercial plant was about 1/100th of the radiation you would get from a typical spent fuel assembly from a power reactor. So it wasn't a lot of activity. There's lots and lots of chemistry examples that people have used in industry in areas of photochemistry on commercial scale, where they've made things using particularly UV lights, a common source. And photochlorination is done, sulfochlorides is done, nitrosylation is done. These things are produced commercially using usually UV light, but everything you can do with UV light, you can do with gamma rays. And potentially, they're a cheaper source of photons. What you really care about is what the dollars are per ionizing radiation unit. And for example, Toray used to make cyclohexanone for making nylon. They had a very large commercial facility in Japan, and the only reason they shut it down was because the electricity costs for running their UV lights got to be so prohibitive, because the electricity prices in Japan are now very high. So one of the big trends in chemical engineering over the last decade has really been a move toward what they call process intensification. And this, I think, is a real opportunity for new thinking about how one would make use of radiation chemistry and processes. And the idea is to combine lots and lots of unit operations, because each one of those little boxes represents capital costs, and combine steps and make one reactor or one unit operation do what many did before. And making methyl acetate is a good example. What took a fairly large plant with lots of different unit operations can be done in one reactive distillation column today. And so you combine steps, you make the capital costs come down, and so you can change the normal scaling relationships, which make people spend a lot of money on capital projects because you needed the scale to make it work, and you can actually build things at smaller scale that still make a lot of money if you're clever. So when you look at thermochemistry on chain reactions, for example, the rates are going to be proportional to temperature, and if you have an initiation step that's fairly high, that rate's going to be determined, or you're going to need to get a temperature that's high enough to have your initiation rate high enough to get drive the overall reaction at an acceptable commercial rate. If you add in a radiation source, you change the kinetics a little bit, and you can speed up that initiation step, and then the other steps thermochemically may proceed quite well and quite quickly at much lower temperatures. So you have the opportunity to lower the temperature that you run reactions. And the thing that's nice about that is that means you can run it in say a distillation column, something that would have taken a lot of energy and a lot of heat to run under normal conditions. If you can speed it up a little bit using radiation, then you can in fact have significant process improvements. So in the case of the ethyl bromide, it was a slightly exothermic reaction. You still have to remove a little bit of heat, and thermochemically, though, it operates very, very efficiently at low temperature. And in fact, the Dow process was really a reactive distillation. They ran it at very low temperatures where they could separate the ethyl bromide very easily, and they irradiated it, and they got enough rate because they were using radiation to initiate it. You can also run uphill reactions if you put a little bit of heat in. As long as the thermochemical steps that are in between the initiation and the final product are sufficiently thermochemically advantageous, you can still, and especially if you pull off a product in a reactive distillation, you can drive reactions uphill as well at quite acceptable rates at much lower temperatures than if you had to initiate them with thermochemistry. So if just as an example, in a halogenation reactor, if you should show the comparison to a thermochemical reaction where the initial initiation step is all thermochemical, you can increase the rate by increasing the temperature. But if you give a radiation kick to it, say a factor of 10 over what you would have had from the thermochemistry, you can lower the temperature for the same reaction rate by about 200 degrees Kelvin. And that gives you significant process help, not only for rates, but also for byproducts. You limit the number of byproducts that you'll be making. So you have a better process, a cheaper process that can really be operated at less expense. And so this idea of using kinetic control to minimize byproducts is widely done. I mean, you oftentimes will run a chemical process at a temperature that doesn't necessarily give you the best rate, but it gives you the lowest byproducts. And that's because you're favoring reactions that are kinetically driven, and you're not pushing it to thermodynamic equilibrium, which gives you byproducts you didn't really want. And so this is done all the time, but normally when you do it with thermochemistry, you pay a price and rate. So when you look at single-pass conversions from regular thermochemical reactions, you look at the yield, which is the product of the selectivity and the conversion, and the yield's going to be what translates generally into your productivity or your profitability of the process. And so single-pass conversions are typically above 20% or so for a commercial reactor, but if you add radiation, you can shift to higher yields at lower temperatures than you could have done thermochemically. And this is what gives you a potential advantage for certain reactions using radiation chemistry. So in the Gen 4 designs, the one design that we happen to like for potentially making use of some of this is the molten salt reactors, because you're carrying the activity around all the way through the primary heat exchanger, and so you have lots of access to very, very high activity loops that you can put in approximation to chemical systems. Also, when they do the online processing, you're going to be pulling out the xenon and krypton in real time, and just the xenon and krypton alone gives you enough gamma ray energy to run a pretty decent sized chemical process. So typically you might be able to get 8%, well, roughly 8% in a power reactor of the reactor power isn't gamma radiation. You can probably get 1% or so of that with reasonable design. And you'll be looking at probably 5 to 10 kilowatts of gamma radiation per megawatt thermal of a reactor. So you have lots of opportunity to get access to this radiation. Now with molten salt technologies, there's lots of challenges. In some ways it's a nice system because chemically, chemical engineers like to pull things out of molten salts because we have ways of extracting and using electrochemistry to pull out the fission fragments. The problem, of course, is the corrosion and some of the other things. But we run processes today in the chemical industry in molten salt environments. Just the coolant in phthalic anhydride is a molten salt, high temperature, hugely exothermic reactor. In fact, more power generation per meter cubed of reactor than a typical nuclear reactor. And we run this all the time with molten salt. So we know how to do this. The liquid-liquid extractions are also done all the time, so these kinds of things are quite familiar to the chemical industry. So getting these things to do online reprocessing is not something that's a reach in technology, and that people have been doing it for the nuclear space for some time. I won't talk too much about this. So in our approach for the problem is really to start small scale, because I think the idea of using reactors right off the bat is probably not realistic. But there are technologies that are out there today. Gamma radiation is used all over the world for sterilization. It's used, in fact, in Australia, 20 minutes from our campus, there's a commercial irradiator that we visited that irradiates the imported items that the customs people don't seem to like. When my wife and I were moving to Australia, they unpacked everything we brought, and they identified of our entire household 4 pine cones that they insisted that we either pay $150 to dispose of, or they would gamma radiate them for $1,600. So, and this was operated by high school graduates, but this wasn't a sophisticated operation. And subsequently, we've got the costing of it. It was built by a Canadian company, and we know how much it costs. We know how much it costs to operate, and it's not very expensive. So you can get sources of gamma radiation to do studies to actually cost out a chemical process that you could do today. And licensing it if it can be licensed in Australia, it can be licensed anywhere. Moving to spent fuel, you have other opportunities to do that. And in fact, there's even a scenario where you can imagine turning a spent fuel pond into, rather than a money-losing operation, into a money-making operation. Someday, probably not in my lifetime, you might imagine using the reactor itself as a source. But first of all, you have to show that you can do it with other sources. Spent fuel is particularly nice in some of the newer designs. These pelleted reactors that in China they're looking at have a nice place where you're going to be pulling out hot pellets. It's almost a chemical engineer's dream, where you bring these right through a reactor. You've got hot fuel coming out, lots and lots of activity, and currently they aren't going to do anything else with it, so you might as well make chemicals. Spent fuel bundles are ripe for utilization if one can imagine a plan. A typical power reactor fuel bundle, they get 60 assemblies per year per reactor. Each one's about 15 kilowatts, 1 to 4 years after shutdown, and those are about half gamma ray. So from a watts per meter squared, if you simply wanted to convert that into visible light photons and use solar cells, you've got 3,000 watts per meter squared, which is 3 times the maximum sunlight. So I'm not advocating doing it. I don't think it's a good idea, but people want to worry about capturing 1,000 watts per meter squared from the sun. They can get 3,000 watts per meter squared 24/7 from a spent fuel bundle. There's lots and lots of, you guys probably know this better than I do, there's lots and lots of activity in spent fuel, and in the US anyway, we have 12 billion curies that are receiving absolutely zero value, and it's only a negative value in watching it. So we've been doing a study right now using as a basis for costing what a commercial facility would cost for irradiating food. And we're working with ANSTO. They've shown that the distribution, energy distribution and penetrations and so forth of gamma or cobalt-60 sources are pretty similar to their spent fuel bundle. So they've measured their spent fuel, at ANSTO, and we have a pretty good correspondence, so it's not a bad model for that. One of the systems we're looking at is making a relatively small scale divinyl benzene process. Okay, divinyl benzene is $4 to $6 a kilogram. It's made today by dehydrogenating diethyl benzene. Takes high temperature, very low pressure for the reactor to drive it forward. Then you have to separate it. You got to go to high pressure, low temperature. So it's a pretty bad thermodynamically limited process. But they make it anyway because the product is so valuable. The best stuff you can buy, which is from Dow, has about only 50% of the active divinyl benzene. The rest of it's the vinyl ethyl benzene, which is not as active, but that's what they live with because they can't make it any better. And it still goes for $4 to $6 a kilogram. So in a very simple system, which we've modeled in a better way than this figure gives justice to, with a G of only 500, you can readily make dibromoethylbenzene, as well as some monoethyl benzene, but they're very, very simple to separate. One thing nice about halogens is that they're very heavy. So the separation, rather than separating an alkane from an olefin, you're separating a brominated alkane from a alkane, and that's a trivial separation. Easy to do at almost any pressure. So the separation is very easy, low energy consumption, and the dehydrobromination of the dibromoethylbenzene goes to 100% yield. So it's a very simple reaction. So all this stuff can be combined. It turns out into a reactive distillation by combining the oxygen reaction that makes hydrogen bromide back into bromine into a oxyhalogenation in a single vessel. And we've shown that we can do this. And here you radiate basically the middle of a distillation column to make your dibromoethylbenzene. You separate it in the same column that you irradiated in, and then it goes through a really simple, cheap reactor that makes divinyl benzene. Anything that doesn't get reacted goes back to the distillation column. And so if you look at this at 1.5 kilotons per kilowatt of gammas, assuming G is 500, which is what we've measured, you're looking at making $7.5 million per year per kilowatt of gamma radiation. So if you were to take, say, an SMR, make 50 megawatts of thermal energy, you're looking at $12 million a year revenue. If you use only 1% of the gammas available from that SMR and you made divinyl benzene, you'd be making $150 million a year in revenue from divinyl benzene. And that would be a scale that would be pretty big if I tried to use all the gammas. And so if I used all the gammas, I'd be making 750 kilotons. That's too big. So I downrated it to only 75 kilotons, and I'm still making far more revenue than you could ever make with electricity. The cool thing about this from a learning and student project and just science point of view is that this is a fairly unexplored area. You get to couple radiation transport with chemical reaction theory. There's lots of stuff that hasn't been done in very, very high dose rate chemistry, where they applied it in particular to try to make valuable chemicals. So there's a lot of unknowns, a lot of things that we don't know, and we have modeling tools today that they didn't have back in the 1960s. So we can do a lot more theoretical work in this area. So it has lots of interesting basic problems that one could look at. When you change your point of view to, rather than saying what's going on in fuel corrosion, to say how can I make use of this radiation field to make something that makes money. Another example is sulfochlorides. Methane is probably, if you go, in fact I have done this, if you go to any major scientist at Shell or BP or Exxon, they'll tell you the first problem on their list is methane. What do we do with methane? We have boatloads of methane. It's going to be here for many, many decades. How do we make use of it, especially when it's at relatively small scale? Well, what we do today is we build a huge plant because that's the only way the scale works, and we reform it to make either methanol or hydrocarbons. But if you can do things on smaller scales, which would fit better with biomethane, for example, if you believe in that, or coal seam gas, there's smaller fields that you can have zero value methane for almost forever. Things like sulfochlorides become very interesting, and people have piloted a UV sulfochlorination-driven process and making 9 tons of carbon with just a simple 180-watt mercury lamp. Again, you can do all this, and sulfochlorination has been demonstrated with gamma rays at very, very high Gs. This pilot had a G of 1,000. So methane is a real big win. The one we're looking at for large scale would be styrene. It's a $30 billion a year business, 25 million kilotons per year and growing. So this scales basically with the world GDP, use of styrene. Basically, it's the same process as making divinyl benzene, but they do it on a bigger scale. You're doing dehydrogenation, so you're fighting equilibrium, high temperature, low pressure, and you have to separate it with low pressure, high temperature, or low pressure, low temperature, and that's a very costly process. Lots of recycle, and it's extremely expensive. Lots of byproducts because you have to do it at 600 degrees C. So it's true, you make byproducts when you irradiate things with gamma rays, but you also make byproducts when you heat something to 600 degrees C. So everything has byproducts, it's just the conditions here are not very favorable for doing reaction chemistry. So this is one we've modeled also with radiation reactive distillation using ethylbenzene. Nice thing about ethylbenzene is it has a single product, bromoethylbenzene, easy to separate, and then again, the dehydrobromination gives you the olefin. And we've done some experiments just confirming that we have very high yields, G of about 500 at room temperature. So when you look at the things that you might make with your megawatt thermal energy, if you're going to be making electricity, you have a long way to go to get the capital to ever make any sense at all. If you want to make fission fragments into isotopes, you have a potential to make a lot of money, but you can only do that for a little while until the market's saturated. With commodity chemicals, though, you have a much bigger opportunity to make valuable things for a long period of time. And so anytime that G is greater than 10, which isn't really that hard to do, your chemical revenue, if you look at typical chemical product values, is going to be bigger than your power revenue. The reason you don't want to make hydrogen is because it's sort of the worst thing you can make, and the best G you're going to get is probably going to be about G of 3 or 4. So hydrogen is the lowest value thing you can make, so your chemical revenue is going to be about the same as your power revenue. But you want to go with Gs of 100, you're going to be making a lot more revenue from the chemicals than from the power. So with one large 3 gigawatt thermal power plant, you can at most make $750 million a year in power revenue. That's if you're lucky to get a good contract, government subsidized. But if you only use 3 megawatts of the gammas from that, you can make a 1,000 kiloton world scale olefin plant. And these things are spent, people build these all the time, spending $10 or $20 billion a year. So they're something that people spend money on today, large value. And they, by the way, also, if you're going to build a $10 billion olefin plant, you have a 100 megawatt power plant on there anyway. So you need power anyway. And so the complexity of that plant, which is very complex anyway, is not going to be changed dramatically by integrating a reactor to that. So the message that I want to sort of leave with people who are interested in this kind of thing is that there's a whole world of space in this mid-range commodity chemical area where you have value that's potentially greater than the power revenue, and you can build a lot of them. The capacity is large enough that you could, in fact, fund a credible development program to make a power reactor that's suitable for this. Let's say that you wanted to develop a molten salt reactor. You're never going to be able to build a business case that says, I'm going to make electricity to do this. But if you said, I'm going to make first, in my first generation, my pilot, I might make some isotopes. In my second generation, first small-scale power plant, I'm going to make a pretty valuable chemical. In my big one, I'm going to make another chemical. If you stage it that way, all along the way, the investors aren't going to be losing money, but they could, in principle, make a little bit of money. So I'll summarize by saying that, I still believe, in the end of the day, the reason I'm doing all this is because I think nuclear power is something that the world should have, and in particular democratic countries should be leading the way. The reason that they aren't doing it is because democratic countries are generally market-driven, and people will not invest in something that's going to be simply a money loser. It's not economical today. We have lots of competition from fossil fuels, and rather than simply acquiescing to that and just saying they need to do the right thing and develop nuclear because it's great, which is what we as an industry have tended to do over the years, I think that accepting the world as it is, which is a competitive marketplace where we have to do things that are economical, and get smart young people to come up with processes that would actually make somebody money is the most likely way to move forward. And co-producing chemicals is potentially a way to do that, using the unique radiations that you can get from a nuclear reaction. So I think it's incredibly rich for innovation in an area where smart young people can do a lot better than certainly I've done and they have been done up to date. So I'll leave it at that and take any questions.
Thank you for a very interesting and stimulating talk. Is this open for questions? Yeah.
Just what, do you see a potential stumbling block with this with regards to how radiation-induced chemistry can be very complicated and you might have potentially more byproducts that you need to separate? Is that a potential concern generally in this area? I mean, is this going to be just something that will be only used for a handful of certain chemicals produced?
Well, again, in the world, the three major organic chemicals are ethylene, propylene, and styrene. And then one of the nice things about halogen processes, iodine and bromine in particular, the cross sections for those are so much higher. And this is demonstrated. They're selective. I mean, you can irradiate the hell out of these. And so if you just made propylene, ethylene, and styrene, you've made 98% of the world's chemicals already. So I don't believe it necessarily has to be a niche. I also believe that people haven't even begun to test the waters yet. I think, I know I don't know the whole field, and I've talked to people who've done radiation chemistry most of their life, and they've been very problem-focused on areas that were related to chemical reaction. I think if we get a different way of thinking about it, for example, we're doing some experiments now in liquid chlorine ICL combinations, and at minus 22 degrees, we can get methane activation. And again, methane doesn't have that many options. So I think that the answer may be, yeah, there's no choice. There's no good options. There's a few niches, and that's it. I don't believe that I can say that today, and I don't believe anyone alive knows the answer to that. And I think it's worth looking at, because what we're doing now, making power, isn't working. So I guess that's my answer. And I'd like to, I mean, part of my reason for being here is to stimulate some discussion. I had a nice discussion with Simon Pinbolt, because I think that you guys have a great facility to do some of these studies of dose rate dependence. I mean, there's a lot of things that one can do where we don't understand at these very high dose rates what goes on, especially if you fill as a thought experiment, if you just take pure bromine liquid and you irradiate that, the lifetime of those radicals is unknown. Now, if you happen to have a little bit of hydrocarbon in there, it's a simple separation. Methane isn't soluble in bromine, but if you inject it in the bottom, you irradiate it, the bromine radical lifetime is likely very long. So it's going to be there until it finds a methane. And you only have one product, which you can control by residence time. So it's not like, it's true if you happen to be in there for a long time, but this is where the combination of reactor design and radiation chemistry, you need to do the two together. You can't just in isolation work on the radiochemistry, because otherwise you'll get frustrated and think, oh, I'm going to make these byproducts. But if you can control your contact time, a bunch of things that I don't understand, but I think that there's a room to look at it. And if I just pick divinyl benzene, which we've already explored in the laboratory, we're costing that system. It looks pretty good, actually, just using a commercial cobalt-60 irradiator. It's a unique one, though. Not a lot of things worth $4 to $6 a kilogram. But I think there's a lot of other ones out there. We haven't tried very hard. Phenol's another one. Phenol's G probably isn't all that high. But hydrogen peroxide, which is pretty simple to make, can't make it at high yield, but even if you've got a G of 10 on hydrogen peroxide, the industry would love to make small-scale hydrogen peroxide. It's a big hassle to make hydrogen peroxide. It's expensive. It's a dangerous process for commercial production. If you could make a small-scale hydrogen peroxide generator, make 50% solution in water, that's something valuable. And I think that the more we're able to show that nuclear technology isn't a black hole where we pour money down it all the time, instead it actually brings value to economic prosperity of the society, then people are going to like it more.
I'm not a radiation chemist, but like in the styrene process and these byproducts, don't you have problems with polymerization as a side reaction that clocks up your? You
do, but styrene thermal dehydrogenation also has polymerization. Whenever you have an olefin at temperature at 600 degrees C, you have potential polymerization. The thing is that if you have the cross-section of halogens, bromine and iodine in particular, is so much higher than carbon and hydrogen, so it's true, you will have some byproduct. You're doing this in a distillation column. It's a matter of playing the game. How much byproduct can you tolerate? I don't know the answer. I haven't done it in scale that's large enough to know if that's going to kill you or not. But certainly the scales that we've done it so far, we get pretty high selectivity. The other thing that I didn't talk about is if you're worried about some of these fragmentation reactions, you can always step the gammas down by putting in plastic scintillators that will step it all down to a UV energy that's big enough to produce radicals from the halogens, but not big enough to start to polymerize. So you can play games, again, using the fact that this unique energy. I think that we have to focus on using. It has to be something that's uniquely valuable. If you go to heat, you're done.
I just want to say that polystyrene and styrene in general is actually one of the things that are used as a radiation shielding. So they're actually
For neutrons.
Yeah, for neutrons.
Yeah.
Maybe not gamma.
Well, they use it because the hydrogen cross-section is so high,
Yeah.
but it's not because of the gamma cross-section is nothing. You don't hide behind a polyethylene wall to protect from...
No, of course not for the gamma, but what I'm saying is that they're fairly stable. They use it in
Yes.
combination with lead. That was my point.
Okay.
They're-
But it's when you have that aromatic, though. I mean, the point's well taken. I mean, there's going to be byproducts, and I think understanding those and suppressing. And I'll give you a tidbit of one of the things I just don't know, and I can't explain, but I'll tell you it anyway. Is we're working on propane and bromine, and when we do propane, hydrogen, bromide, oxygen, and we irradiate it, we get a fair amount of byproducts. We add a pinch of iodine. Suddenly the byproducts go away, we make propyl bromide, period. I don't know why. I mean, I can speculate the iodine scavenging, I can come up with some mechanism, but I don't understand it. Nobody does. No one can write down, of course that's because the iodine's doing this. It's an area that's unknown, and I think that's what's sort of fun about it, is when you're intentionally trying to control the kinetics. And we're much better now. We can build a reaction network that includes almost all of these steps, and we can model it and say, okay, what things might we want to make? And we can do a lot of this stuff in silicon and theoretically before we go to the lab. There's some things we're going to exclude because we know we can calculate transition states of some of the thermochemical steps, and we'll say, it's going to have to be too hot anyway. We might as well just use thermochemistry. But I think we can do a lot of sorting and sifting and find the sweet spots now because we have tools that they didn't have before.
So if you use a scintillator, aren't these tin compounds? I don't know.
There's polymer scintillators that are pretty good.
Oh, okay. Because I was thinking there was going to be...
In fact, we're doing an experiment right now, though I'm not a big advocate of doing photoelectrochemistry, but just because we wanted to do it to show we could, we built a matrix out of polycarbonate, which is a decent scintillator, and we built these little, silicon junctions inside, and so we'll make some hydrogen and oxygen. It's a gee whiz experiment, but it shows the point that you can use scintillators to convert to band gap energies of photons.
Mm-hmm. So there was a question. So, man. Yeah.
I can see this as definitely being a proven technology at lab scale. Do you see, or how would you see that transfer from lab scale to process scale? Is that going to be a real challenge that we need to address?
So the good news is I believe anyway that you can pilot it with UV, high energy UV. So, because by every measure, I'll use the diethylbenzene case, we've shown that with UV irradiation, we get basically the same byproduct and product yields as we get with gammas. So I would build the pilot with UV, and I'd pilot it, give the byproducts, and then we can cost it. We're really good at costing processes, and in fact, that's one of the things that the Dow Centre does. I mean, I've brought in as my team are process engineers who have experience in costing chemical, because our view is that you don't go to the lab until you've shown on paper that it's worth going to the lab to do an experiment. Because if in the end it doesn't matter what your conversion and selectivity is, it's not going to work. There's no point in going to the lab and measuring it. But we'll go and so, for example, with this case, we know what the G is that we need to make this thing valuable, to make it work. And thankfully, we've already shown that the G was high enough. What we don't know yet is the trace byproducts that might be something that would be why you would go to pilot anyway. I mean, in any chemical process, you pilot it so you can measure the small byproducts that build up in the recycle loop. So but I think we have almost enough to make a convincing story to build a relatively small scale pilot And the nice thing is that because these gamma radiators are around, you can in fact go to many facilities and do a pilot in their gamma radiator.
You're concentrating on alternative feedstocks, and I think it's because of the Dow connection. But one of the classical application areas is making polymers. Have you explored that realm as in combination with maybe SMRs or new reactor technologies too?
No, I think that's a great question. We actually, because Australia is big in LNG, and so someone's already went to the trouble of liquefying methane. And so now you have this big pipe with liquid methane in it. If you think about all the products that you could make from methane would be solid actually at that temperature. So you could, I've gone through the thought experiment. There's data actually from back in the 40s or something where they were doing liquid methane irradiation experiments for different reasons. They were trying to look at lifetimes of radicals and stuff. But there's reason to believe that in that environment, if you added a sensitizer, you could in fact make some pretty interesting things, polymers and so forth. And then you could capture them because liquid-solid separation is trivial. So you could capture this solid out of that liquid stream, and someone else spent all the capital in making it liquid. You would never build a liquefier to do this, but if someone already did, pulling out some solid fraction, even if it was a relatively small fraction, and the rest goes off to the LNG world, you still made money. So we have thought about it. It's just a difficult experiment. We're actually picking the ethylbenzene, to be honest with you, is because I can do it in room temperature in a lab. It's just to do liquid methane experiments, to do some of these other things are much bigger budgets than I have to work with. So we thought about them, but now the one thing we are doing, back to this polymer idea, you have to also ask the hard question, is the reactor really the best source, the cheapest source of energy? I mean, if you have a high enough G, you could maybe afford to use another source. I mean, at the end of the day, it has to be a cheaper source. Electron beams are pretty cheap. Per unit of ionizing radiation, electron beams are hard to beat. The problem is you can't get an electron beam into a steel vessel 3 meters in diameter. Mm-hmm. So gammas are going to be a win when you want to try to use a standard operation like a distillation column. If you want to do radiation reactive distillation, gammas will win cost-wise because introducing electron beams into that is very difficult, or pressure and things like that. But if you have a thin sample, in fact, even flue gas has been treated with electron beams, and it's not so expensive. Electron beam systems, when I started to write the paper, I'm thinking, oh, gammas are going to win. But it turns out electron beams we've got real costs on these things. They're not very expensive. They're really cheap. And they use them for commercial processing all the time. And they're very efficient to boil off. You can steer them. But to get them into a pressure vessel, you've got to go through a tantalum window that's very thin. And if you put any energy through it, it melts the tantalum. So it's a complicated way of introducing it into a volume reactor. So it's only going to be advantageous to use gammas if you're looking at high pressure conditions where you'd want to use a steel vessel. And right now what we're trying to do is look at a cost comparison for that piece of hardware that you need to introduce an electron beam into a reactor, because that ends up being a pretty expensive piece. And where's the break points? What scale? At a certain scale, gammas are going to win, always.
Yes.
But small scale, I think electron beams win. Even with gas phase reactions, at small scale, I think electron beams are the best. But anything at scale, and that's why I tend to like these things like styrene, at least from an extrapolation point of view. It might be better to make diethylbenzene with electron beam. But I want to be able to make a case. Again, my goal for doing all this isn't to make diethylbenzene or even styrene. I want to have a pathway so that the chemical industry wants to participate in this space to help bring some of the things that they're good at, which is lowering process costs, to the nuclear industry, which is terrible at lowering process costs. And between the two of them, I think they can make this work. I think if we stick it to the pathway that we have historically with the nuclear industry, they've never had to make a profit. They always are subsidized. They always get special benefits. They don't compete on a world environment. And if you get some of the thinking of cost reduction, good engineering, and innovation, and reducing costs, I think the chemical industry can bring a lot to it, and the nuclear industry can bring a lot to the chemical guys. And that communication, though, I think is really important, and that's what we're trying to do at the Dow Centre.
Do you think the world is ready for this? I personally just tried to make a proposal of new innovative technologies, and it was using radiation in nuclear areas, and it didn't go anywhere.
But was someone going to make money?
Okay.
Someone
I didn't tell them they're going to make money.
I mean, one of the things that I think that I spoke with this at your your nuclear manufacturing group, is bringing together a group of young people and give them the task of building a box based on nuclear reactions that makes money. You know, that I think is the real challenge, is showing that somehow this, and I believe you can do it. I believe that, for example, with a molten salt fast reactor design, the core is nothing. I mean, the core is a trivial design for this thing. It's geometrically critical. The heat exchanger, we know how to cost that extremely well. It's a phthalic acid heat exchanger, so I know how much that costs. That vessel cannot be very expensive, and you could stamp these things out. So there are designs, if you go into it knowing it cannot cost more than $500,000 per megawatt, if you know that's what it has to cost, and you put that constraint on it, T equals 0, suddenly you're not going to be doing light water reactors anymore. It just isn't possible to build a pressure vessel that cheaply. And so it makes you think differently, and unfortunately in my generation we've already been put in these blinders to think along a pathway that I think is not proven to be successful.
I like pebble bed reactors, and you showed the tree, so that's my favorite reactor.
And actually the molten salt.
And I like that, and you can put them through when you have to renew them anyway, and put them through your reactor, so you can have a stream in your cycle that's.
And you just use molten salt for the coolant. Don't use gas. Then you don't have a pressure vessel.
Yeah.
Why do you think that it is twice as expensive, basically, from your costings to build your reactor in the US than in China? Like, do you think there needs to be a switch in the safety? I personally think it's to do with safety concerns. It's public perception of building a reactor. I think we're over.
There's a great book to read that I highly recommend. This guy named Marin. He wrote a book called Industrial Mega Projects. And you read this thing and you'll be very depressed, because it says basically that any project...
So you're recommending this?
No, I am, because it will make you think that this idea of process intensification has value beyond just making things cheaper. Being able to make a smaller project have a financial win is really important, because what this book says is basically any project over $1 billion has a 50% chance of failing from T equals 0, because there's so many complexities that you don't think will happen that happen. You build a big refinery. They built it. They built bajillions of them. They should know how to cost that exactly, but in fact they will get the price wrong by a factor of 2 for sure. But why? And if you go through this, they'll tell you things like, they'll require that you build a hospital as part of the project. So you build a hospital, but then something happens at the hospital. All kinds of things happen. And so what you have to do is change the game a little bit. If you can make something work at 10 kilotons, which you can build in a factory, then you suddenly now eliminate a lot of these extraneous things that come back and haunt you. A good example is when they build these offshore oil platforms. They build these in the Houston Ship Channel. They build them in these, almost it's a factory really that builds them. They get the cost down. They're actually produced it cheaper than the estimates usually. They get them done faster than they estimate, and it's because they have this cookie cutter design.
Yeah, it's modulation of everything. I do a business enterprise course as part of my PhD where we've focused on effective product manufacture and design and stuff, and how to cut costs and get everything better, and modularization is. And
you've got to do it up front. You've got to do it up when you're actually. That's why I'm a big believer of giving some young people a clean sheet of paper. This idea that nuclear fuel has to be in rods was there because we were collecting plutonium for weapons. I mean, the value proposition for the nuclear industry was to produce plutonium. It was a chemical production plant. That's what a reactor was. As an afterthought, they made some power from it.
No, of course, and I think there was better designs for reactors earlier on that never got funded, and they never continued to do research because they didn't produce plutonium, and there was no.
There was a driver in engineering the economics of size, and they made things big because it made them cheaper. And now we're moving away from the economic size, the economics of modularity, and this is going to change how things are done. What I find especially interesting is what you usually hear about is using the heat that you put off. Generation 4, one of it is using the heat for things like making hydrogen. It's not worth it there.
You can make heat cheaper with coal.
Yeah.
Coal's hot. It burns hot.
Yeah, but it's not carbon.
It doesn't matter. It
carbon
doesn't matter. No
neutral.
one cares about carbon. It doesn't matter.
You're going to be utilising the heat anyway, but you're still going to produce electricity, right? So there will still be the heat's not just going to be wasted into the air sort of thing. So.
Yeah, you'll use the heat more efficiently if you maybe do some thermochemical stuff. But the real advantage is to use the thing that's unique. Again, is use the radiation because it's special. If you have to compete head to head with kilojoules, you just don't win.
So the things to increase the economics, you hear two things. This is using the heat and then improving our grids. And this is a whole area that isn't talked about very much, of using the unique part for other processes and combinations. I like it.
Because I mean, in some ways, it would be great if just once a nuclear process would make money, just once. And then it will catch on a little bit. But if every single nuclear project is a money loser, which they have been, then why would anyone want to do it? And so if you make even a small reactor that just made doped silicon, I think the idea, and maybe some of the students would be interested in, form a team and build a business plan around making money using a nuclear reactor.
I wish I was doing the energy yes again. You do this energy I did it last year. We didn't have a good idea. This would have been a fantastic idea to try and build you have to build a business plan around based about an idea that will save energy or is a next generation of energy. We picked solar wrongly. We tried to think of something nuclear, but we couldn't think of anything, and this would have been great because it would have been a way to make money and price it. Yeah.
Well, when I teach the engineering economics course, and I just say, okay, well, if you're making a product and you have a certain amount of inputs that cost you money, you have a finite amount that you can spend on the box. It doesn't matter what the process is. And if the output is power, you cannot spend more than a certain amount. It just doesn't work. And if you're going to if the product is more valuable, you get more capital to spend. And that's what you want to do, is you want to be able to have more flexibility on your capital. And if in the end you do good things for society, which is in my mind what I'm really motivated for, I have to get society to do the right thing by showing them they can make money at it. And at the end, I believe that you can make, I actually believe I could design a molten salt fast reactor that would be cheaper than a coal plant to make power, just competing on heat. I believe that's possible. None of the designs that people are looking at right now are designed with the basis of making them low cost. They're all designed for other... And this whole idea of proliferation resistance should be just rejected, because no one is going to make a weapon out of 25% enriched fuel. That is just ridiculous. It's so ridiculous. And the fact that the scientific community hasn't just said that, how ridiculous that is.
Oh, we do. So we don't get listened to. There's at the University of Manchester, there is a group called the Hitchhiker's Guide to Nuclear. Do you do that? Yeah, I've been on like the podcast and stuff, and it's a group of students who have sat down and said this is absolutely ridiculous, and they have thousands of followers globally who listen to the podcasts every month. I don't know if they're still monthly, but they used to be all month that did it, and they discuss this thing, and you get different people's opinions on it, and it's all younger people, and sometimes they get lectures into talk and stuff.
In part, you have to convince the academics, because I have many friends who are very prominent physicists who will argue adamantly that solar panels are going to be the solution, and they'll tell me why people can make weapons of it. I said, well, walk me through this. So tell me how this guy is going to come into this plant, get this 25% enriched fuel with much plutonium in it, carry it, take it someplace. I just don't see how this physically is possible. I mean,
you need a legion of people who want to do this together.
Yeah, I mean, it's just such an unrealistic scenario to worry about it. Because if you can use a little bit of enriched fuel, then you're going to be able to drop the price down to nothing. And this idea that we have to fixate on this not making any plutonium is ridiculous. Just burn the plutonium, make some plutonium, and burn it. It's a good fissionable nucleus. And the idea we can't is nutty. I mean, it just puts unfair boundary conditions on the problem. Now, if you can always go to the thorium loop, which is okay, but if you want to make a cheap reactor.
But don't you think someday the driver is going to be cost, and people will want a cheap reactor, and until that happens, nothing's going to change?
Well, I think that now, I mean, there are people in the world that actually are going to adopt nuclear, and they could care less what the U.S. says. I mean, India is going to do that. They're going to, and they care about cost. So I would collaborate with.
They're looking into thorium because they have so much thorium, so it's a different world.
If the issue is just being stuck in your ways and the political involvement, really, is because the policies, the energy policies are their policies. They're not just somebody. And our government won. France did. They went, well, nuclear is the way forward for right now. It's what we need to get our energy prices down. And just went and built.
But if there was a lot of money to be made, I think all of this would go away.
Of course.
The reason that there's all this stuff is that no one wants to change it because no one's going to get rich changing it. So if they change it all and they build PWRs, then no one's going to get rich on this because they're expensive. Your profit margin is almost nothing. So why would you want to do it? You're going to get rich making coal plants. And so, but if we can show them a way that they can get rich making nuclear plants.
Gas plants.
Huh?
Gas plants they're cheap.
Yeah, and gas plants. But coal and gas plants are both cheap and money makers. So if we can, I think our real goal as a community is to show a hard-nosed investor who simply wants to make money, and there's lots of those around, show them how they can do that using a nuclear process. I think that's how all this stuff will go away. But no one's going to go down to their congressman and say, your rules are stupid, if they don't have a lot of money to make. They pay off senators because they make a lot of money doing something. So magically regulations go away when somebody's going to make a lot of money. But if no one's going to make a lot of money, why would they want to take the regulations away?
No, I agree. It's rather depressing.
Well, no, I actually look at it as a challenge. Let's figure out a way to make it worth their while. So that you can, and that's why I had great faith or hope anyway that Bill Gates would do something with TerraPower, because here's a guy who understands this. The problem is they shackled themselves with this traveling wave reactor that looks basically like a light water reactor, fuel rods, the whole business. And so in spite of, they didn't have a clean sheet of paper. They brought in, old-time reactor designers who made it look just like a light water reactor core and same, boron control rods, and that was it. And now they're going to try to reclad the reactor.
They're pretty much the only reactor designers that are still around. Are they old?
No, there's lots of young guys. I mean, I have my students at MIT are doing. They're actually building a very nice reflector-controlled solid core fast reactor. But the problem is they're trying to sell it for power. Their business models. They're going to go sell it to the military for forward operating base power. You have a customer equal to 5. They don't care about the cost. It will never be commercialized. Why are you doing this? So there are young, and at least their design was clever.
Is there a big trust gap though, sometimes between scientists and general public with new reactor design? So you can tell the government that this is the way to do it. This is the best way we should do it. We should allow these reactors to be built by the or privately. But then the people go like, oh, I don't like that. We don't know what's going on. It's a new product. Don't trust you.
But this is why clever people like you need to think of ways around it. No, but go I'm serious. Go to South Africa. Build your first one in South Africa, where it's a much more receptive environment.
But they even can their pebble bed reactor.
Yeah, but for money, for cost reasons, not because of if there was going to be money to be made, they would have built it. But there was much cheaper for them to build a coal plant. And so show somebody they can make a lot of money, find a place to pilot it, and build it and do it, and then the rest of the world will catch on. But if you try to use the system as it exists today, it's so prohibitive. You got to go around the system and come up with a new way. And so for us anyway, that's why we're going to take the approach that will show that we can make chemicals in a commercial cobalt-60 irradiator, because those aren't going to be, they're going to be below the regulatory radar screen. But that won't help us get power reactors online. But at least it's just where people will see, hey, I can make money making radiation. By the way, these guys who are selling these commercial radiators, the people who are using them for food irradiation are making a boatload. I looked at their balance sheet. If you look at what they cost per hour to irradiate a pallet of stuff coming off
those pine cones.
But also even the commodity things like tomatoes. They're all the exported tomatoes and papayas from Australia to New Zealand get irradiated. That's part of the deal. But the markup on that, the differential that you're making on pre-irradiation, post-irradiation isn't very much. So they're not making a lot on it, but their balance sheet is fantastic because they're moving these things through very quickly. So using radiation to do things that are productive and make people money.
ANSTO's spent fuel, did you use directly that, or was that just a case?
Well, we just compared it to the cobalt. They measure. They have a whole a map of their spent fuel bundles that they measure the doses and stuff on. So they just mapped it to the. We also have spectral.
So this was a paper study. You didn't actually try to do.
No, they're happy to do it. We can use the cobalt 60 array. The reason for that was just to show that the cobalt 60 array was a good analog for it. It was good enough.
But do you think that it would be a good way to utilize all of the spent fuel that we have instead of reprocessing it and letting the reprocessed products just sit there doing nothing?
It depends on the cost, right? Because at the end of the day, you say, okay, if I'm going to just use the gamma radiation, is it cheaper to go buy a cobalt 60 pellets and use those?
It shouldn't be about whether
But they're in cooling ponds anyway. They're just sitting there.
Yeah, so could you utilise the facility where they're sat just in the cooling ponds doing their thing? You could convert a cooling pond because the penetration that's going to be big enough if you change the pond size to be able to provide the gamma radiation and the part.
Well, here's a business model for you that I actually believe is viable. You know, right now, the spent fuel pond is a cost for the power producer. He has to maintain it. There's a cost. So I'm your Nuco company, and I go to the power guy and I say, look, I'm going to manage your pond for you, and I'm going to do it cheaper than you're doing it now, and you just pay me the service fee for it. So that means the guy's paying you to manage his spent fuel pond. Now you bring in your stuff, and you make extra money because you're using that spent fuel to do something else. I think that actually could work. I think that if you had to go buy and transport spent fuel to another place.
I wasn't suggesting that.
Yeah. But I do think there is a business model where you can do that, where you as a subcontractor would run your spent fuel pond. Yeah, they have no interest in making money. They have some of these casks.
We know,
it's
terrible.
They have casks that have 100 kilowatts of gamma dose, and you could use that even for water sterilization for wastewater treatment. If it's just wasted, you can imagine lots of things to use it for, because and they're not cheap, those vessels that they have. So the addition of a water loop around it or something like that, it's all going to be the differential cost from what they're doing already. Anything that you can do to make money. Now the amount of money that's going to be compared to their $2 billion a year loss is probably small, but if you're a private contractor and you're able to extract that, it may not be significant in their budget, but it might be a business for you. Each case has to be looked at on a cost-by-cost basis, and that's why we went down this pathway of looking at, and by the way, really high-value stuff where you don't care about the cost of the photon aren't the place to go. That's why the commodity chemicals are kind of nice, because you do care a little bit about where the cost of the ionizing radiation comes from. It's not an insignificant part of the process. For something that's so valuable like these pharmaceuticals, if you have to use UV lamps, it just doesn't matter. Your capex doesn't matter. Pharmaceuticals don't care what the reactor costs. Commodity chemicals do. So you only want to do things where it's capital sensitive, and that somehow the radiation is causing you to be able to reduce the capital expense. That's the only case where it works. And that if you have to have OPEX additions, then you have to make sure that they balance. The nice thing about a reactor is that they have a huge infrastructure already. You have all kinds of physical plants, you have all kinds of utilities that you're putting in anyway. So you have lots of shared utilities, you have enough people at a reactor that the staffing wouldn't be an additional cost. So by the time you share resources, your overall cost of this box isn't going to be very different than just the reactor itself.
Because of the shared infrastructure and the shared site, and
because typically the off sites and the OPEX are at least half the price of the facility.
But ideally, if you were thinking of a perfect solution, you'd utilise the waste as well separately, because it doesn't matter what you're doing at the nuclear plant, you're still going to be producing more waste.
Again,
so you still want to utilise it while it's no longer being fissionable.
I'm a big believer in the other reason I like the molten salt is because you're either doing continuous or pretty rapid batch. So you're basically pulling out all these valuable transition metals. You're pulling maximum value. So you're getting isotopes. You're getting all the things you can out of this. And from a salt system, they're much more separable than they are in these silly ceramic pellets that are a hassle to deal with. It's way easier to pull it out of a molten salt than it is out of a ceramic pellet. My view is that you're continuously reprocessing, so when the reactor eventually gets shut down, you don't have a bunch of junk to clean up. You've been cleaning it up the whole time. So there isn't, other than the activated structural materials.
We have tea outside, so you can continue the discussion. It is quite refreshing, but we can have refreshing discussion with refreshment. Yeah? Okay, let's thank everyone.